So let me begin today's lecture by going over, by finding an analog of a very powerful tool in one variable calculus, namely the mean value theorem. Here we don't quite have the exact analog, but we'll get a mean value inequality which will serve the same, which will play the same role in many applications. So to begin with, what we are aiming for in general will be, as usual, I'll have an open set in Rn. It turns out that I'll need something more than just being open. I'll need a convex open set. But for now, let's just say I have an open set and I have a differentiable function with 2Rm. And I would like to get a mean value, something like a mean value theorem. But to do that, first let's look at the case when I just have the domain is an open set in R. As I said, I'll be needing something more than just open. I said convex. In the case of R anyway, convex open sets will be just open intervals. So I am starting with an open interval I. So here I is an open interval. And the statement is the following. So if I take 2 points in the interval, then there exists x in between those 2 points. I'm assuming a less than b, such that norm of fb minus fa less than or equal to b minus a times norm f of x. Such that this, well, that's it. Yeah, there exists x such that I have this. Notice that even in this case, even though the domain is an open interval in R, I still don't have an equality. But otherwise, the inequality is one thing. The other thing is I'm taking norms on both sides. So apart from these two differences, the terms appearing are the same as the one variable case. So let's try to prove this in a very simple-minded way. It actually won't work. So what one might try is, after all, f is a map to Rm. So it will have m components, f1, f2, fm. Each fi will be a map from the same interval into R, a real valued function. So one might think that if I apply the classical mean value theorem to each of these component functions, I should be able to get the result. It doesn't quite work that way. So let's try anyway. So I'll write fb minus fa. And then, so I'll get corresponding components. Then I take norms on both sides. And since it's just the Euclidean norm, I get this expression. Now, if I apply the mean value theorem to each of these things here, I'll get f1b minus f1a is f1 prime c1 b minus a for some c1 in ab not cm in ab. So I'm applying the mean value theorem m times and I'll get this. Therefore the norm will be, and b minus a is the common factor. So I just plug all these expressions here inside this, and I'll end up with b minus a comes out, I'll get sum of squares of various derivatives. But there's a big difference between this and what we are aiming for. What we want is if b minus f a less than or equal to b minus a, norm of f prime x. So which, if you write it out, will have to look like f1 prime x and square of that and so on. So the point is that all these component functions are being differentiated at the same x, which is not the case, which may not be the case if you apply the mean value theorem separately to all of them. So the attempted approach does not yield what we want. So instead we proceed as follows. Now this proof in Rudin is not exactly a natural proof in the sense that it seems a bit of a trick. But anyway, so it proceeds as follows. The quantity we are interested in is fb minus fa, let's call it z. Now here is the part which is not obvious. You define a new one variable function by phi of t is inner product of z with f of t. I'm using this notation, bracket notation for inner product instead of dot. So this is the same as the dot product. So instead of a dot b, I'm writing it as a inner product b. Now when you take dot product of two differentiable functions, it's easy to see just by the definition of the dot product that what you get is differentiable. Here anyway z is a fixed, it's a constant. So on the other side we have f, so the whole thing is differentiable. Phi is differentiable. And the point is this phi is again a map from the same interval, but this time its image is just the real line. So I can apply the classical mean value theorem applied to phi. Gives phi b minus va is b minus a phi prime x for some x and ab. And so I can differentiate from this expression. I can also differentiate phi prime t. There's a general formula for dot product of two differentiable functions in Rn, which again just follows immediately from the definition of dot product and Leibniz rule. Here that gives z is a constant, so I just get f prime t. And I plug that in here. Phi prime x is z f prime x. This is, on the other hand, phi b minus phi a, if I just go by the definition of phi, I'll get z f of b minus z f of a. I collect the terms together. Fb minus fa is again z, so I'll get norm z squared. So when I equate these two expressions, this star and double star, I get norm z squared as b minus a times this thing here. Now, so yeah, that's what I have. Now from here to here, I have used the Cauchy-Schwarz inequality, which is inner product of VW, absolute value less than or equal to norm V times norm W. So this will be less than or equal to z times norm f of x, norm of f prime x. The same z occurs in both places, and we can assume z is not 0. If z is 0, there's nothing to prove. So I cancel off one z here. So I'll end up with z less than or equal to b minus a times norm of f prime x, and therefore norm f b minus f a less than or equal to. This is exactly what we want. So z is f b minus. So as I said, this is like a sort of a sleight of hand or a trick. One can do it in a more natural way as well, but this is the proof in Rudin, so let me just stick with this. And using that, let's prove the more general thing. So now I assume that the domain is an open set in Rn, n bigger than or equal to 1. And I also assume that U is open and convex. I'll just explain what convex means. F from U to Rm is differentiable, and I assume that the derivative of f at every point has operator norm less than or equal to m. Then the claim is that for any 2 points in the open set, I have norm of fp minus fa less than or equal to m times norm b minus a. So let's recall, in case you don't know what a convex set is. Subset in Rn is convex if the straight line segment between, if you start with any 2 points in S, the straight line segment between those 2 points is also contained in S. So formal way of saying that would be, if AB are in S, then the parametrized curve, then the straight line between them can be written as a parametrized curve in this form. This is the simplest way of writing that. 1 minus t times a plus t times b, where t is between 0 and 1. For every t, this should be in S. That's the condition. So note that convex sets need not be open. For example, in R2, I can take S to be the x-axis, or for that matter, any line through the origin or any line wherever. All of them are convex, but they are not open. So let's assume the set is open and convex, and let's proceed. So let gamma t, so I'll take the straight line between those 2 points. These are the points A and B. Gamma t is equal to 1 minus t. I start at, when t is 0, I'm at A. When t is 1, I'm at B. So this gamma can be regarded as a differentiable function from 0, 1 to u. And let g of t be this thing, f of gamma t. So f is going from this open set into Rm, and gamma is from 0, 1 into this open set. So the composition would be from 0, 1 to Rm. Now, by the previous result, so we can get some stuff, but before that, in the previous result, I had an open interval rather than a closed interval to work with. But that's not a big issue here, because this gamma, I can actually take the straight line slightly to the left of, slightly before A and slightly after B, because U is an open set and A and B are points inside the open set. So I can go slightly past the line segment on both sides. So I can actually get a map from minus epsilon to 1 plus epsilon, the open interval. Then 0 and 1 would be points inside that open interval, and I can do what I did. So I won't write that down. Now, by the previous result, there exists, so I'm applying the previous result to G. G is a function of one variable, the target is Rm. There exists X such that G1 minus G0 less than or equal to 1 minus 0, which is just 1, times norm of G prime X. So now let's just calculate the derivative of G using the chain rule. I get G prime T is F prime gamma T multiplied by gamma prime T. Well, in this equation, this is F prime gamma T is a m by n matrix. This is a n by 1 matrix, and this is a m by, left hand side would be a, so this is n by 1, this is m by 1, this is m by n. The thing is that right. One has this nice property that it's a definition of the operator norm, that norm of AV less than or equal to the operator norm of A times the norm of B. So these are Euclidean norms. Norm of V and norm of AV are Euclidean norms. So I'll get, applying this, I'll get Euclidean norm of G prime T less than or equal to operator norm of F prime gamma T multiplied by Euclidean norm of gamma prime T. And since gamma T was the straight line parameterized in the usual way, 1 minus T times A plus T times B, when I take derivatives, I get gamma prime T is B minus A. And I just plug it in, that's it. Norm G prime T less than or equal to, and the derivative of F is bounded by above by M by assumption, and here I'll get B minus A, and well, what else? So then G1 minus G0 less than or equal to M times B minus A, but G1 is F of G, remember G of T was F of gamma T. So G1 would be F of gamma 1, so F of B. F of B minus F of A is less than this. So this is what we wanted. So as a corollary, the corollary is immediate. If U is open convex and the derivative is identically 0 at every point, then F is constant. There exists B with F of X equal to B. And why is that immediate? Well, it's just that this capital M you can take to be 0. You get F of B minus F of A equal to 0 for any two A and B, which is, it says that F is constant. But if one just wants the corollary, one doesn't need to assume that U is convex actually. It's enough to assume that U is connected. This is a problem in Rudin and I have assigned it as homework. You must first note that convex sets are certainly going to be connected but connected sets need not be convex. And in fact, the mean value inequality requires convexity. There's no way of avoiding that. But this corollary doesn't quite require convexity. Just U is connected. It's enough to assume U is connected, and of course always U is open. So I'll stop here, and in the next lecture I'll talk about the partial derivatives. Again, revisit the question of partial derivatives and the full derivative.